Welcome to the deep dive. Today we're tackling something really fundamental to the things we build around us, but it's often totally hidden. Picture, like a huge bridge or maybe a skyscraper, right? We see it as solid, permanent.
Rock solid.
Exactly. But what if something tiny, invisible, could cause it to crack, maybe days after it's finished? Silently.
It's a really fascinating problem, and it pushes right into the core of what we call weldability, how well you can actually join in materials safely, reliably. Some materials, particularly certain steels, are just trickier, need more care.
And that's our mission for this deep dive. We're getting into one of the biggest headaches in welding, hydrogen-induced cold cracking. Everyone just calls it HICC. You want to unpack what it is, why it happens, and the really important bit, how engineers and welders actually stop it from happening, keeping our structures safe.
Yeah, the prevention side is key.
Okay, so let's get into this hidden threat, hydrogen-induced cold cracking. That's the full name. But it's got other descriptions too, hasn't it? Ones that hint at its sneakiness.
Definitely. Cold cracking is a big one. It tells you straight away this isn't happening when the metal's hot and glowing. Nope. These cracks show up after things have cooled down, sometimes quite a while after.
That delay, that sounds like the tricky part.
It really is. And then there's where it happens. It's not random.
Right, you mentioned a specific danger zone.
That's the heat-affected zone, the HAZ. It's the metal right next to the weld that didn't melt but got hot enough for its internal structure, its microstructure, to change. That's the prime spot for HICC.
Mostly there, but not always.
Mostly, yeah. But you can sometimes find these cracks in the weld metal itself, too.
And this delayed cracking aspect, that's pretty unsettling. It's not like you finish welding, look at it, and say, okay, looks good.
Not at all. We're talking hours, sometimes even days later. The window is generally considered up to about 72 hours, which, as you can imagine, makes inspection challenging.
Yeah, I bet. A ticking time bomb, almost.
It can feel like that sometimes. And you mentioned other names. Sometimes you hear underbead cracking when it's in the HAZ, right under the weld bead. And if it is in the weld metal, occasionally you get these chevron cracks.
Chevron, like the pattern.
Exactly. They form at about a 45-degree angle, kind of arrow shape. It's quite distinctive when you see it.
So, given how, insidious this is, what materials are we actually worried about here? Is it all metals?
No, not all. It's mainly a problem for certain types of steel. Your basic carbon steels, carbon manganese steels, and then a whole range of alloy steels, low, medium, high alloy.
Okay.
Generally, we're talking about steels that have a ferritic or martensitic structure. Things like HSLA steels, high-strength, low alloy quench, and tempered steels, TMCP steels, basically steels that can get quite hard if they cool quickly.
That makes sense. It's useful to know what's susceptible, but also what's not, right?
Yeah.
For context.
Absolutely. Knowing where you don't usually see HICC is important for design choices.
Right.
It's very rare in duplex stainless steels, for example, and you just don't find it in nickel alloys or copper alloys.
Good to know. So material selection can be first line of defense sometimes.
It can be, yeah, if the application allows for it.
Okay, so we know what HICC is, this sneaky delayed cracking and where it tends to happen. But the real key for fixing it is understanding it's not just one thing causing it, is it? It's more like a perfect storm.
That's a perfect way to put it. It's the absolute bedrock principle for preventing HICC. It only happens when 4 specific conditions line up at the same time.
4 conditions, all at once.
All at once. And the power in knowing that is, if you can break the chain, if you can eliminate just one of those conditions, you stop the cracking. That's where all the engineering controls come in.
Okay, so it's like a 4-legged stool, take one leg away and it falls over.
Precisely. And often, dealing with the hydrogen is the most direct leg to target, but the others are just as critical, especially with tougher materials or tricky designs.
Right. So what are the 4 ingredients for this perfect storm? What needs to be present?
Okay, number 1, you need enough hydrogen. The threshold is generally considered to be above 15 milliliters per 100 grams of the deposited weld metal.
15 milliliter per 100 grams. Got it. That's the hydrogen level. What's number 2?
Number 2 is stress. You need significant tensile stress in the weld area, specifically stress that's greater than about half the material's yield strength.
Half the yield strength.
Yeah.
And that stress comes from the welding process itself.
Mostly, yes. Residual stress. It's just inherent from the heating and cooling, the expansion and contraction. And in joints that are held rigidly, what we call highly restrained joints, these stresses can get really high, sometimes right up to the yield strength.
Okay, hydrogen stress. What's the third factor?
Third is temperature. The cracking generally happens when the weldment is below about 300 degrees Celsius. If it stays hotter than that, the hydrogen can usually move around and escape more easily.
Below 300 C. Okay. And the final piece, number 4.
The fourth is a susceptible microstructure. This means the heat-affected zone, that HAZ we talked about, has become hard and brittle.
Hard and brittle. How hard are we talking?
Typically, we look at hardness values. If the Vickers hardness, HV, gets above around 400, that usually signals a problem. It indicates the presence of a microstructure called martensite.
Martensite. Sounds sharp.
It is. It's a very hard, needle-like structure that forms in some steels if they cool down really quickly. It's strong, but it doesn't have much give. It's brittle.
So, recap. High hydrogen, high stress, lowish temperature, and a hard, brittle structure. All 4 needed.
That's the recipe for disaster, yes.
It really highlights the interplay, doesn't it, between the material itself, how you weld it, the whole thermal cycle.
Absolutely, it's all connected.
But how does hydrogen, just a tiny H atom, actually do the damage? What's the mechanism?
Right, so it starts with hydrogen entry. These hydrogen atoms are the smallest atoms there are. They can get into the molten weld pool really easily. Usually they come from molecules containing hydrogen breaking down in the high heat of the welding arc.
Where do those molecules come from?
The big culprits are moisture water, H2O. Moisture hiding in the coating of welding electrodes, in flex cord wires, and the flux used for submerged arc welding. Even tiny amounts can release a lot of hydrogen.
So keeping your welding consumables dry is crucial.
Absolutely critical. But it's not just consumables. Moisture in any rust or scale on the metal surface, or oils, greases, paints, any hydrocarbons left in the weld area can be a source too. Even cellulose coatings on some electrodes are a big source.
Okay, so hydrogen gets in. Then what?
Then it's about diffusion and trapping. When the steel is really hot, those tiny hydrogen atoms can zip around quite freely, diffuse through the metal lattice. A lot might escape into the air.
But if it cools down too fast?
Exactly. As the temperature drops, especially below that 300 C mark we mentioned, the hydrogen atoms slow down. They can't move as easily. If the cooling is rapid, they get trapped inside the steel, often gathering at little imperfections like grain boundaries or tiny voids, particularly in the HAZ.
Trapped.
That trapped hydrogen causes embrittlement. The precise physics is, well, complex and still debated in some details, but essentially the hydrogen weakens the bonds between the metal atoms in those localized areas. It makes the steel lose its natural ability to deform slightly under stress, its ductility.
So instead of stretching a tiny bit, it just cracks.
It cracks, especially when you have those high residual tensile stresses already present. The hydrogen creates these weak points, these internal notches almost, and the stress does the rest. It's a really damaging combination.
Wow. Okay, that paints a clear picture. So knowing those 4 conditions and how hydrogen works, the prevention strategies must focus on breaking that chain, right? Taking out one of those 4 legs of the stool.
That's exactly the strategy. You target one or more of those 4 factors.
Let's start with the obvious one. Minimizing hydrogen. Since it's hydrogen-induced cracking, seems like the first place to look.
It usually is the primary focus, yes. We know the sources. Moisture influxes, maybe cellulose, contamination on the joint like rust, scale, oil, grease.
So practically, what do welders do? How do you keep hydrogen levels down?
It starts with the consumables. You have to use low hydrogen consumables where required, and then you have to keep them low hydrogen. That means proper storage baking electrodes as per manufacturer instructions, keeping them in heated ovens, quivers until use. Using vacuum-sealed packs helps too.
So handling is key.
Handling is huge. For basic saw fluxes, they're often stored in heated silos. You limit how long electrodes are exposed to the air, you make sure wire spools are covered when not in use, and critically, the joint itself must be clean and dry, absolutely free of any rust, scale, oil, paint, moisture.
Even the shielding gas in processes like MIG or TIC matters.
Oh, definitely. The dew point of the shielding gas, basically how much moisture is in it, needs to be very low, typically below minus 60 degrees Celsius. It's another potential hydrogen source, if not controlled.
I've heard different welding processes themselves have different inherent hydrogen levels. Is that a factor in choosing how to weld something?
A massive factor, especially for critical applications or high-strength steels. There are standards, like BSEN 1011-2, that classify consumables based on their potential hydrogen content, using scales from A down to E.
A being high hydrogen, E being very low.
Exactly. Scale A is over 15 milliliters per 100 gram. Scale E is under 3 milliliters. And different processes tend to fall into different ranges. TIG welding is usually the lowest, often scale E, less than 3 milliliters.
Yep.
Then you have processes like MIG, MMA with basic low hydrogen electrodes. Maybe ESW, they can often achieve less than 5 milliliters, say scale D. Submerged arc welding might be under 10 milliliters. Scale C. Flux cord wires can vary. Some are low. Others might be up towards 15 milliliters, scale B or A, unless specifically designed and controlled to be low hydrogen.
So choosing TIG over, say, a standard SCAW could be a significant step in reducing hydrogen risk.
It absolutely could, yeah. But TIG is slower, maybe less suitable for thick sections. There are always trade-offs: cost, productivity, suitability for the joint.
Right. Always balancing factors. Okay, so controlling hydrogen is strategy 1. What about number 2, reducing that tensile stress? You said it's inherent, so how do you manage it?
Yeah, stress is tricky because, like you say, it's always there from the welding thermal cycle. How much stress you get depends on things like the thickness of the steel, the heat input used, the type of joint, how big the whole component is.
How restrained it is.
Exactly. If the parts being joined can't move freely as they heat and cool, the stresses build up much higher. Getting stresses above half the yield strength, especially in thicker sections or complex geometries, is pretty common. Direct control is hard.
So what can you do? You can't just wish the stress away.
No, you can't, but you can try to manage it. One way is through design, avoiding sharp corners or features that act as stress concentrators. Think about poor fit-up between parts or a sharp transition at the edge of the weld, the toe. Those are bad news.
Smooth things out.
Smooth things out, ensure good fit-up, minimize the root gap. Also, sometimes applying a heat treatment after welding, a stress relief heat treatment, can significantly lower those residual stresses.
That's post-weld, though. Anything during welding?
During welding, sometimes adjusting parameters helps, like increasing travel speed can sometimes lower the overall heat input for a given weld size, which might reduce stress slightly. Keeping the amount of weld metal deposited to a minimum helps too smaller weld, less shrinkage stress.
Makes sense.
And simple things like making sure the joint isn't excessively clamped or restrained. Sometimes you can even preset the joint slightly, anticipating the shrinkage. For very critical work, sometimes dressing the weld toes, grinding them smooth while the joint is still hot, can help reduce stress concentration right where cracks might start.
Lots of little things that add up. Okay, hydrogen, stress. Now the third piece, the susceptible microstructure, the hard, brittle HAZ.
Right. So a susceptible microstructure is basically one that's too hard, usually because it contains a lot of that martensite phase we talked about. For typical carbon or CMN steels, if the hardness in the HAZ gets above, say, 350 HV, you start getting concerned about HICC.
And what determines how hard the HAZ gets?
Two main things control the maximum hardness: the steel's chemical composition and the cooling rate of the HAZ after the weld pass goes down.
Composition, that's where that CEV number comes in, right? Carbon equivalent value.
Exactly. The CEV is like a shorthand way to estimate the steel's hardenability based on all its alloying elements. Carbon is the most powerful hardener, but manganese, chromium, molybdenum, vanadium, nickel, copper, they all play a role. You plug the percentages into a formula.
Don't need the exact formula, but the concept.
The concept of simple: higher CEV means the steel has a greater tendency to form that hard martensite structure when it cools, so higher CEV means higher risk of HICC, all else being equal. It tells the engineers, okay, this steel needs more precautions.
More susceptible. And the other factor was cooling rate.
Cooling rate is critical. The faster the HAZ cools after welding, the more likely it is to form martensite and become hard.
What makes it cool faster?
Two main things again. Lower heat input from the welding process means less heat overall, so it cools faster. And greater joint thickness, thicker metal pulls heat away more quickly, acting like a bigger heat sink.
So for avoiding hardness in typical steels, you want to slow the cooling down.
Generally, yes. For carbon or carbon manganese steels, slowing the cooling is a key strategy to avoid excessive HAZ hardening.
How do you do that?
Well, first, if possible, you might specify a steel with a lower CEV, but often you have to work with the material specified for the job. So, more practically, you control the welding procedure. You use a moderate level of heat input, not too low, which cools too fast, but also not excessively high, which can cause other problems like grain growth. And the big one is preheat. Heating the steel before welding slows down the cooling rate afterwards. And if it's a multi-run weld, you also control the inner pass temperature, the temperature the joint reaches before the next weld bead is laid down. Keeping that inner pass temperature up ensures the cooling stays slow.
So preheat helps with cooling rate and maybe driving off moisture.
It does both, yes. It's a very powerful tool.
But you mentioned low alloy steels are different sometimes.
They can be. Some low alloy steels, particularly those with significant amounts of alloys like chromium, molybdenum, vanadium added for strength at high temperatures, for example, they're designed to harden easily. Their HAZ might become very hard almost regardless of the heat input or preheat you apply within practical limits.
So controlling the microstructure becomes much harder for those.
Much harder. For those steels, controlling the microstructure leg of the stool is less effective, which means you absolutely have to focus even more intensely on controlling hydrogen and maybe stress and definitely temperature. That's why they are often more prone to HICC.
Right. It forces you to rely more heavily on the other prevention methods. Which brings us neatly to the fourth factor, controlling the weldment temperature itself. How does temperature play a role beyond just influencing the cooling rate and microstructure?
Temperature has a direct effect on hydrogen diffusion. Remember how hydrogen gets trapped when it cools below 300 Celsius?
Yeah, it can't move around as easily.
Exactly. So if you can keep the weldment warm above that sort of critical range for long enough after welding, you give that trapped hydrogen a chance to diffuse out of the steel before it can cause embrittlement.
So it's about giving hydrogen an escape route.
That's a great way to think about it. You're managing the temperature profile over time to facilitate hydrogen removal.
And how do you do that in practice? You mentioned preheat already.
Preheat is key here too, obviously, because it slows cooling and raises the starting temperature. Typical preheats might be anywhere from 50 degrees C up to maybe 250 C, sometimes even higher for very sensitive steels, depending on thickness, CEV, and hydrogen level.
And maintaining inner pass temperature helps keep it warm during welding.
Correct. But there's another step, particularly important for thicker sections or higher risk steels: post-heat.
Post-heat? That sounds like keeping it hot after you finish welding.
That's exactly what it is. You maintain the preheat temperature, or maybe even increase it slightly, say to around 250 C, and hold it there for a specific period after the welding arc is extinguished, often for at least 2 hours, sometimes longer.
And the goal is purely hydrogen removal.
Primarily, yes. It's giving that hydrogen time to diffuse out while the steel is still hot enough for it to move easily. It's important to distinguish this from post-weld heat treatment, or PWHT, which is done at much higher temperatures, like 600 C or more, mainly for stress relief or tempering the microstructure. Post-heat is a lower temperature hold, specifically targeting hydrogen.
Got it. So preheat, inner pass control, and post-heat are all about managing temperature to slow cooling, influence microstructure, and let hydrogen escape.
They all work together to break that chain of 4 conditions.
But you touched on heat input trade-offs earlier. It sounds like a real balancing act.
It absolutely is. You want enough heat input to slow the cooling sufficiently to avoid excessive hardness and help hydrogen escape.
But not so much heat that you damage the material properties.
Exactly. Too much heat input can lead to coarse grains in the HAZ, which can reduce toughness. It can also lower the yield strength. Too little heat input, as we said, leads to fast cooling risk of hardness, hydrogen trapping, and also potentially welding defects like lack of fusion.
So finding that sweet spot in the welding procedure is crucial.
It's where the skill and knowledge of welding engineers and qualified welders really come into play, especially with demanding materials and applications. It requires careful calculation, often using standards like EN 1011, and precise control during welding.
So wrapping this up, what does this mean for you listening? When you see a big welded structure, maybe that bridge or building frame, or even something smaller like a pipeline join, you see the final product. The strength.
The solidity.
But knowing about HICC, this hydrogen cracking, it really drives home the immense amount of, well, diligence and science that goes into making sure it is strong and stays strong. It's not just sticking metal together.
Not at all. It's a constant battle against these invisible factors. Material science, careful procedure control, meticulous cleaning, temperature management, all these hidden layers of effort are there to prevent something like a tiny hydrogen atom causing a delayed failure.
It's quite humbling, really.
Yeah.
So maybe a final thought to leave you with. When you look at that welded structure now, think beyond the surface. What invisible challenges like hydrogen cracking are engineers and welders constantly managing behind the scenes? How many layers of hidden diligence are built into the world around us, ensuring safety and making sure things last, often long after the people who built them are gone?